All right, students, we are on page 17, section 4.3, sum and product of roots and conjugate zeros. So let's get right into it. I think we're going to skip this review just to refresh real quick. We're not going to do this all the way through. But if I tell you something has roots of 1, 2, and negative 4, I know the factors would be x minus 1, x minus 2, and x plus 4. And we could multiply those through if we wanted to, and we could get our polynomial. So we're not gonna bother with that. Here's our first idea: the conjugate zeros theorem. If polynomial p has real coefficients, and if the complex number z is a zero of the polynomial, then its complex conjugate is also a zero of the polynomial. So what that tells us, if you think about, if you were to solve an equation using the quadratic formula or completing the square, at the very end, you would have something like this: 2 plus or minus, and then this could be anything. Let's say it's radical 7 over 4. This plus or minus, it's always in the formula, right? It never goes away. So unless this radical 7 part, unless this is like a perfect square, so if that was 9, it would be 2 plus 3 divided by 4 and 2 minus 3 divided by 4, and that's your answer. But if it's a square root, an irrational number or an imaginary number, let's say it was like I radical 7, these complex numbers have to come in a plus and a minus pair. It has to. That's the only way that formula works. So, for example, if 4 plus 5i was a root, that means absolutely without a doubt 4 minus 5i has to be a root. It has to work that way. So just a little bit of foreshadowing. Let's say I now wanted to turn 4 plus 5i and 4 minus 5i into factors. So just like let's say x equals 4 was a root, x minus 4 would have to be the factor. So if 4 plus 5i is the root, then x minus 4 plus 5i is the factor. And if 4 minus 5i is the root, then x minus 4 minus 5i is the factor. And then I could distribute that negative through, and the factors would be a little bit nicer, not really nice, but a little bit nicer. They would look like this: x minus 4 plus 5i. So here's what we're going to do today. We're going to learn a little shortcut here. If I wanted you to turn this into a polynomial, so with real coefficients, to get rid of those i's, we could multiply that through, and the i's would cancel each other out, basically. They would go away. But we'd have to multiply a trinomial by a trinomial, and that would just become kind of a mess. So I'm going to show you a little shortcut, and this may be something you've seen last year, maybe not: the sum and the product of the roots. Sum and product of the roots. So let's say I'm going to put an equals 0 here. I want you to find the zeros or the roots or the solutions of this polynomial. So nothing to it. We factor. We have x equals negative 7 and x equals 3. So what your Algebra 1 teacher probably told you back in the day was, they said once you get the factors, you can just change the signs. So that was like a little shortcut that you learned. You probably know, well, you know why that is the way it is now. But here's what's interesting about that. So if I take my two roots, the negative 7 and the 3, and I add them together, if I find the sum, negative 7 plus 3 is obviously negative 4. And I'm going to write it as negative 4 over 1. If you look at how this relates to your original equation, the sum of the roots, that negative 4 over 1, is the b value, just with an opposite sign. So if you think about like back in Algebra 1, again, you would think to add to a positive 4 and multiply to a negative 21. So if we're looking for numbers that add to the positive 4, but then we switch the signs when we're finding the solutions, it makes sense that if I add my solutions together, it's going to be the opposite sign of my b value. So this formula, this sum of the roots, if I add my roots together, it always gives me the b value just negated over whatever the a value is. And in this problem, the a value is just 1. So the sum of the roots, if I add my roots together, it tells me exactly what the b value is, just the opposite sign. And the product of the roots is even easier. If I take -7 times 3, that equals -21 over 1. And you can see right there, -21 is my c value. So the sum of the roots, if I know the roots of a function and I add them together, that tells me what the b value in the quadratic function is. Just negate it. And if I multiply the roots together, if I find the product, that tells me what my c value is. And then if they have a denominator, if they have a common, a value here in the denominator, that tells you what the a value is. All right? So formula, the sum of the roots is -b over a. And the product of the roots is c over a. So once we do a couple of these, that will make a lot more sense. All right, so what about a function with roots of 3 and -2? This one, you don't really need to do the sum and product of the roots. What we could do is just, you don't have to write this, but we could just turn these roots into factors, right there. We could multiply it. We would get x squared minus x minus 6. So that one, you wouldn't need to do that formula. It's really easy to multiply. But just to show you how it works, the sum of these roots, 3 plus -2 is 1. The product of these roots, 3 times -2, is -6. So you can see I could take those values. The b value would be -1, which it is, and the c value would be -6, which it is. So it's a little bit of a nice streamlined process when we're looking at a question like this. So find an equation in standard form of least degree that has roots of 4 and 2 plus radical 5. So first thing, here's my roots. X equals 4, x equals 2 plus radical 5, and don't forget the conjugate pair. X equals 2 minus radical 5. So what we could do to find this polynomial, I could do x minus 4, careful here, x minus 2 minus radical 5, so turning these roots into factors, and x minus 2 plus radical 5. If you don't want to learn this new process, you could multiply those together. You could do a trinomial times a trinomial, like I said. You could go to your windows if you need to, and you'd be here for a few minutes. It's not the worst thing in the world, but there's an easier way. We can use this sum and product of the roots process. So looking at my roots, I have 2 plus radical 5, I have 2 minus radical 5. The sum of those roots, and this is why it works, this is why it's so nice with these irrational and complex roots, 2 plus radical 5 plus 2 minus radical 5, those radical 5s go away. They add to a 0. So my sum is just 4. My product, 2 plus radical 5, 2 minus radical 5, that's great. We already see the pattern. This is a difference of 2 perfect squares, really. So we have 4 minus 2 radical 5 plus 2 radical 5. So those radical 5s go away again, and we're just left with 4 minus 5, which is -1. There's the product of the roots. So we're done. That's my answer. That should be an equal sign. I have p of x equals x minus 4, and then I can turn these two complex roots into a quadratic really quickly. So it's x squared. My sum is 4. So in the formula, my b value is -4. And then my product is -1, so that's all there is to it. Now, I didn't give you a point to go through. I didn't tell you specifically what to do, so we're just going to leave it there. We can multiply it through. I did that for you because I know you guys can handle that. So there's how we would find our polynomial. And I just changed it from a p to an f, whatever. You guys know what I mean? So it just streamlines the process. So let me go to the next page. Let's see what I want us to do here. Why don't you guys do number 2? I'll pause and let you work on it. I have my work done. So just to see how you did. If you are lost, you can just wait for me to unpause it, and then we'll go through it together. So pause now, try it out. We'll talk again in a minute. Okay, so hopefully you paused and gave it a shot. So there's my roots. X equals 1/2, x equals 3 minus I, x equals 3 plus I. I mentioned this last time, it's a lot easier when we're doing our multiplication to turn that 1/2 into a 2x minus 1. You don't have to, but it's nice to do it sometimes, make your life a little easier. And then I would encourage you to get a little practice with this. So we do our sum of the roots, we do our product of the roots. Side note, just in case we didn't mention this in class, I squared, if you recall, is equal to -1. All right, so that's what I did right here. Sum of the roots, product of the roots. So my sum is 6, my product is 10, and now we're set up. I still have my 2x minus 1. My sum is 6, so it's a -6 in my quadratic, and the product is 10, so it's just a 10 in my quadratic. Okay, so pause if you need to look at this more closely, but I can distribute, combine some like terms. And then the one thing I did tell you for this, I did tell you we have a y-intercept of 20. So I know the point 0, 20 is on my graph. So I can plug in 0 for all my x's. I plug in 20 for my output. And we really don't need to do too much of a y-intercept check on this one, or an a-value check. To get this -10 to be a positive 20, I just need to multiply everything through by a -2. And there's my function. So we'll have some time to practice this next class for sure. Let's see, I also did, was that number 2? Oh, right, there's only 2 on this page. All right, if you want, you can take a look at number 3 on this page. So you can pause here. I'm not going to go through it, but that's just my rough work before I didn't even multiply it all the way through. And if you also want, you can look at letter C on the next page. So I was a little more meticulous with this one. So I'll leave this one up for a second. You don't have to practice it. If you want to, just to try it out, you can. But we will do some of these next class. We're not going to spend a ton of time on it, but we will spend a few minutes. So take a look at letter C. Respond to the questions in the Google form that goes with this video, and I will see you guys next time. All right, so let me know if you have questions. Talk to you soon. Bye.